Hi, ladies and gentlemen, welcome back. Our next talk will be about deploying machine learning models in Python. The speaker is Albert Auer. Albert is currently a machine learning lead engineer at Swoop, an e-commerce startup in Hong Kong. He was involved in various projects in data mining and machine learning while being a researcher at Huawei North Arc Lab, S3, and NTT Communication Science Laboratories in Japan. He has a PhD in computer science from the University of Southampton. Albert has been programming in Python since 2004. He is also a part-time lecturer at the Chinese U of Hong Kong, teaching courses related to Python, machine learning, and network programming. Now let's welcome Albert.
Hello. So thank you for having this opportunity to give a talk. So my name is Albert. I'm now working as a machine learning engineer. So in this talk, I would like to share a little bit of my experience as a machine learning engineer in deploying machine learning models. So what is this talk about? So first of all, we'll talk about the need to deploy machine learning models and what do we mean by deploy. We'll also discuss about different kinds of workflow in machine learning projects, and also what are the common strategies to deploy machine learning models. And then, of course, we are in a PyCon, so we talk about how we can do that in Python, and some other considerations. But we will not talk about, for example, using Docker or Kubernetes, because those are more on the DevOps side, which is not my not my expertise. But anyway, I hope this would help some of you if you are working in the area of machine learning engineering. So I think if you are interested in machine learning, or if you have ever done any machine learning project, you will know what is Kaggle, right? So Kaggle is a website where you can enter machine learning competitions. You are offered like a machine learning data set with some test data. So you train your model, whatever model you like, maybe combine 1,000 models together for ensemble, and then you generate predictions on the test data. And then you upload to the website, and then you see where you are in the leaderboard, right? So everything is actually great for data scientists and machine learning researchers, because you don't need to prepare the data, right? You have everything download, and then you just load it from a CSV, and you can, all you have to do is to focus on building your model or models, right? So this is great, but there's one thing that this is not very, not exactly the same in the real world, because you only focus on building your model offline, right? So you build your model offline, and then you generate predictions in batches, okay? So you generate all the predictions for the test data, and then you upload. So this is about building machine learning models offline. But in the real world, you might have to make your machine learning models available to other people. For example, you work in a large company. There is a huge system. Of course, there's an IT system which does not only involve machine learning. It might involve other kinds of things. Machine learning is only a small part of the system. So in that case, you need to have your machine learning model available to other people to use. So you can't just build your model offline and generate some data. And so this is not the end of the story. So that's why in practice, when we talk about engineering a system, ML model training is only a very small part of the whole project. So we can consider a system like recognizing handwritten digits. So everyone doing machine learning might have done this using TensorFlow before, right? You have written digits images, and then you try to train a model to classify them into 0, 1, 2, 3, 4 to 9, and then you might do some evaluation, and then you have the model, right? So if you do things in a Kaggle way, then you just focus on the left-hand side. But then the model, the purpose of the model is to make sure that in a real-time system or in any production system, you can correctly recognize handwritten digits. For example, scanned from a file or from an envelope, etc. Right? So we also have to focus on the right-hand side, right? So the first thing is, after you have trained a model which is sufficiently good when you test offline, you put it into an online system. So it will be a part of the system, and then when input comes, you generate predictions, and then you generate the output, right? So that is on the right-hand side why if we have a system on the right-hand side, then you have to think about how do you deploy your machine learning models. So we can classify machine learning project workflows into several different types. Of course, I'm not very exhaustive here because depending on the nature of the business of the company or your project, it might involve different things. But generally, we can classify things into these three types. The first type is you train it offline, and then you also predict offline, basically batch processing. I give you 10,000 rows, you generate 10,000 predictions. And then you store all these predictions in a database or somewhere, right, such that it can be used later in the future. The second way is you train an offline model, you put it in a device, which is called embedded device in most cases, and then you just put it in the wild and use it as a machine learning model to generate prediction. The third one is after you have a model, you put it into a service. Right? It can be a network service, a networking application, and then allow other components to actually send requests to your service to request for predictions. Right? So in this case, we are all talking about training a model offline. So we are not talking about online learning, etc., which is possible in some cases. So we can go through each of these scenarios briefly so you have a better idea. So the first thing is, for example, something like a recommender system. If you go into Amazon, of course, this is not exactly how Amazon does that, but just as an example. So you want to generate recommendations to a group of users, right? So you have their profiles, you know how many things they have bought in the past. So you can actually, for each of the user, you pre-generate a list of recommendations of books or things that they would buy, and then store it in a database, right? And then when the user comes, you just go to the database and get the list of recommended items. So you can randomize it a bit so that the user, every time he comes, he sees something different. But essentially, you don't have to generate predictions at real time. So this is the first case. The second case is something that you will see, for example, in a drone, right? Nowadays, drones are very powerful. They can detect a person, they can track a person or any object that are moving, and that kind of things, right? So a lot of computer vision models that are embedded in the system. So if you really have to build something like this, then we probably have to train a model offline and then put the model into the system and in the computer inside the drone, right? So of course you cannot expect the drone to be connected to the internet. Every frame it captures will be sent to the internet for prediction and then come back. This would be a lot of time delay, right? So what people usually do is they put the model inside the system into this drone. And then when it is in operation, it will generate prediction by itself, right? So no networking is needed. And then we come to the last workflow we just mentioned, which is you train the model offline, and then you package the model as a file or something that you can send over to other people, right? And then make this model available as a service, either as a network application or HTTP endpoint, something like API, and then allow other component or users to send requests to this service and then generate prediction. So an example would be something like the example I just mentioned, handwritten digit recognition. Another example is, for example, spam email detection, right? So on the left-hand side, this would be something what a data scientist would do, right? He collects some data, he trains the model, try to tune the model such that it achieves acceptable accuracy. And then he packaged the model such that it can be put into an online system, okay? So when some email is coming, It will go through the model, and you can predict whether it is spam or not spam. Right? So the focus will be on how can we make something like the machine learning surface on the right-hand side, in which you put your model, and then you can generate predictions. So especially in the use case of 2 and 3, we have to think about how to deploy. And by deploy, we mean that basically we put the resources into a position that it is available to other component or users to use. Right? So it's not like that you can just hand the model file to other users, because in that case, the other user will have to write a program, load the model, and generate prediction by themselves, which is not desirable in many cases. Right? And in this talk, we are not going to talk about embedded system, because I personally am not very familiar with that, but I have some experience with use case 3, so I would like to just share some of my experience. So there are actually 2 common strategies to do that. The first one is during the research and development phase, you use whatever tools you like to train your model, right? TensorFlow, PyTorch, scikit-learn, etc. And then the first strategy would be you try to find a common or standard format that try to describe your model. So one of such standard would be PMML, which is predictive model markup language. So it actually is something like XML, but it describes all the model parameters in your trained model. And then you can actually put this into another application which is written in another language. For example, Java application can read this kind of predictive model file. And then in the Java application, once you prepare the input, you can feed that into the model. And then you generate the predictions in real time. Okay? So on the left-hand side, that would be what data scientists are doing. Right? They use Python or maybe even other language to generate the model, to train the model. And then on the right-hand side, we have software engineers focusing on building the system that make use of the model to generate prediction. So that would be the first case. The second case would be maybe we want to also control a lot of things by ourselves, because in model in training model and generate prediction, we might have to preprocess the data. Right? For example, if you test data, you might want to do some tokenization, entity extraction, etc. If it's image, then you might want to do resizing, controlling the brightness and contrast before fitting into the model. Right? So if that would be the part of your model, then you might want to have some control yourself. Right? So, and this kind of preprocessing cannot be easily packaged into a PMML file. So in that case, we can simply use Python all the way down. Okay? We create an application in Python which deploy the model and allow others to send requests and to ask for prediction. So that would be the 2 different kinds of ways to deploy machine learning models. So if we want to use the first method, then there are actually some libraries available now. For example, if we use sklearn, we have a package called sklearn to PMML. So it is actually very easy to use. And it supports quite a lot of models and feature extraction modules in sklearn. So here's an example. You can, for example, let's say we are doing text classification. So first of all, we use Count Vectorizer. We tokenize your sentence, and then we use logistic regression. It's just a simple linear model. Okay, and then we predict whether for example, it might be spam or not spam email. And then what you have to do is, after you train the model, you can use sklearn to PMML to output a PMML file. And then this can be shipped to a Java developer, right? So the Java developer can load the model in the Java application and then make use of the model. Right? So this is one option. If you are using something like LightGBM, there is also something called JPMML, LightGBM, which saves a LightGBM model into PMML format. So these are all quite straightforward. The second way is actually more common because, as I just mentioned, you might want to have some control on the pre-processing or even post-processing. For example, you generate the prediction, and then you might have some rules to filter the prediction, simply because you know that sometimes the prediction is obviously wrong, right? You don't want to output that. So in that case, it might be better if you build a microservice yourself, meaning that you have a Python application, it accepts requests or messages from other component, and then once we receive the message, it will use the model to generate prediction and then send out response. So this would be what the workflow would look like. On the research or development side, you do model training, you do model selection, and then you create a model file. And then when you deploy a system, you try to, inside another Python application, you load the model, and then you can serve the model via different kinds of protocol, like HTTP or TCP or asynchronous messaging, which I will describe shortly. So there are actually a lot of tools in Python available for building microservices and serving machine learning models. So I roughly divide it into 3 different types. And the first one is very straightforward, XML-RPC. A lot of people doesn't realize that this is an option, but in fact, it is one of the easiest way because you don't rely on any other third-party libraries. And then there's a large bunch of HTTP web framework in Python, Flask, Django, Bottle, a lot of things that you can name. And then we can also use asynchronous messaging, which is something like Kafka or RabbitMQ. So we try to go through some of them to give you an idea how we can actually use them to deploy machine learning models. So before, from our experience in using machine learning models and deploying, we think that usually it's better to wrap your model into a class, such that, for example, you can even put your training method inside the class. You can put a predict method which wrap around the original model's prediction function. Because you might want to do some pre-processing, you might want to post-process the prediction output, etc. Right? So wrapping everything into a class will make it easier and it make it separate from the deployment process, or even in the application, it makes it easier for the application to use the model. So this would be a skeleton of what a classifier look like. Right? So when you initialize it, you will load the model which is packaged from the model training. And you can even put a lot of parameters here inside the class, like which data set you use to train, what kind of validation data you use to test the model, etc. So anyone has access to this class can actually retrain the model by themselves or evaluate the model by themselves before actually deploying the model. And if they want to use the model, they simply call predict. And they don't have to worry too much about what kind of pre-processing you have to go through for the data. Okay? So let's assume that we have this kind of wrapper class in our project. And then also a side note on if you are using TensorFlow. So if you're a scikit-learn, then it is relatively simple. If it's TensorFlow, because of the design of TensorFlow, you need a graph when you try to do inference, right, for deep learning models. So one thing that actually, if you search, you will find a lot of solutions on Stack Overflow, but the first time you use it, you will always face this problem, which is when you try to call prediction, it will say that your graph is not there. So the problem is that when you initialize your deep learning model, you should save a copy of the default graph, a reference to the graph, such that when you predict, you will use the same graph to predict. Then you can basically use this in any Python application. So this is some small tips. So the first thing we mentioned is using XML-RPC. So this is actually a very, very old technology. It is built on top of HTTP, and then the message are formatted in XML. So in Python, there is a built-in library. So you can just call the built-in class and functions, and then you have an XML-RPC server, and then you can have a client immediately, which is I think it's the easiest solution if the components that are using the model are also written in Python. So the server will be something like on the left-hand side. So you try to deploy these servers as XML-RPC server. So you first of all, you load a copy of the model, and then you register a function to this server. So in this case, we register the classifies predict function. Okay? So whenever there's a function call to this predict, it will take the input and generate the output. Right? So it can be as simple as this, right? And then you run the server. Then on the client side, if you want to request for a prediction from the model, you simply make a connection to the server and call the function, server.predict. Okay? So underneath it is HTTP communication, a request and a response. But the beauty of XML-RPC is that you don't need to worry about that. Right? So this would be one of the first options that you can consider when you build a simple, when you deploy a simple machine learning model. And if you go online to search how can I deploy a machine learning model, a lot of blog posts would recommend you to use Flask. This is probably one of the most popular web framework for deploying any machine learning models, because it's actually quite simple, but of course it is not always the best choice. But nevertheless, it is a good first attempt or first option. So you create an application, Flask application, and then you can specify a route. So because this will actually create an HTTP REST API. So you can specify that if a request is sent to /predict, then this function will be invoked. Okay, and then you can get the data from the JSON input from the HTTP request, send it to the predict function, and then return the response as a JSON data. So this is how you can use Flask. And one thing to note is that if you use Flask, because it is a WSGI compliant framework, you can deploy it using a WSGI server, such as gUnicorn. Okay? So if you want to have multiple workers running your application, you can also specify that I want to have multiple workers. And then you can receive multiple requests at the same time. There are other frameworks, such as one is called Falcon. So this one, unlike Flask, Flask actually is originally designed to allow you to create web applications, so like web pages. But then if you only focus on delivering an API, then you can choose this one, which is more REST API focused. But the usage is more or less the same. You create a handler function, handler class, in which you can you specify a function when there's a post request or get request, you get the data and call the model's predict function, and then you return the response. And there's a framework that actually I just discovered yesterday, which is actually very similar to Flask, but they use asynchronous communication and asynchronous programming underneath. And they claim to be much faster than Flask. It's like 50 times faster. But of course, it depends on how do you do the benchmark. So it is also worth trying this out. So you see the syntax is actually very similar to Flask. You just define a route and then define the function when you to be invoked when there is a request coming in. There's also one way, which is AIO HTTP. So it's built on top of Async.io, since Async.io is available in Python 3.5. So it's also still very similar. It creates a REST API endpoint where you can receive HTTP requests. But what is special is that it's asynchronous. So if during handling data I/O, it will switch to another task to run other operations. So it might save some time if you have a lot of data coming in and out in your application. So there are several pages online that compare these different kinds of web frameworks. So on the right-hand side, for example, this Vibora framework claimed to be like another order of magnitude when it can, the number of requests it can serve per second. So actually I haven't really tested myself, but it looks like it's very promising. So it's something that's worth trying. But there's also a note from our own experience, which is these kind of benchmark also only focus on how fast they can process a request and send out a response. But in a machine learning application, actually a lot of the time will be spent on pre-processing the data and also doing the inference. If you have a deep learning model, if you run on CPU cores, it might take up to 1 to 2 seconds. So the difference might not be that large, and this might not be that important. So usually we would choose a framework that we're most familiar with. Another thing we want to talk about is we have been talking about web framework. So basically using HTTP, but in some cases, HTTP might not be the best solution because it is synchronous. Right? So imagine that I have multiple servers that are interacting with each other. So maybe service 1 send a request to service 2, and then send a request to the ML service. So in that case, every service has to wait until the task has been finished on the machine learning application. And if it takes a long time, everything has to wait. Right? So if you don't want to wait, if you want, for example, service 1 to do other things while it's waiting, then we can switch something to something called asynchronous messaging. So it's basically building a message queue between all the services such that they communicate via the message queue instead of directly sending message to each other. So there are actually some options like Redis, which is originally a key value store, but it can also be used as a message queue. And more advanced options would be RabbitMQ or Kafka. So Redis is usually used as a cache. So you can specify the value of a key, and then you use it just as a database, simple database. But it has a publish subscribe function, which allows you to use it as a message queue or message broker. So if you want to do asynchronous messaging, you can simply do something like that. On the left-hand side, which is the client side, so he wants to ask for some predictions from the machine learning service. So what it has to do is it submit a message to a particular channel. And on the machine learning service, it simply has to subscribe to that channel to receive message from other service or other components in the system. Then you can call the model predict function once you receive a message, and then maybe you send back the message using a message queue again. Okay, so and then everything is non-blocking. So on the left-hand side, after you publish the message, you can still do other things. On the right-hand side, the machine learning service can focus on processing all the messages. So some similar things can also be done if you use Kafka. So Kafka is much more scalable. It can be deployed even on a cluster. So if your system is very large scale and it has to actually process a lot of messages, then I would recommend you use Kafka instead of as simple as Redis. So these are just some examples on how you can use, so you can create a message producer and consumer for Kafka. So the last thing I want to talk about is when it comes to scaling your ML services. So for example, your model might have to serve a lot of users or other services at the same time. So one thing usually people are doing is that they use Docker and then Kubernetes to manage all their Docker container. One thing we want to stress on is that when we deploy machine learning model, it can be a challenge when you try to allocate resources to each Docker container, because some of the model are actually, they can make use of multi-cores on your computer, like sklearn's random forest classifier, Facebook's fasttext, or if you use TensorFlow and PyTorch, they are inherently multi-threading and multi-processing. So if you use Docker, and if you limit the CPU number to, for example, only one CPU, then you will spend a long time doing the inference. right? There is a process that is needed to tune the amount of resources that you allocate to each Docker container. So in some cases, it might be useful to, for example, you deploy a lot of Docker container in one single machine so that you can gain from the parallelization. But in some case, if the model actually can use up all the cores in your server, then you might be better if you have a single worker and using, for example, asynchronous messaging to consume the message in the most efficient way. So to summarize my talk, basically when we do a production system for machine learning, accuracy, precision, recall are only like one single small part of the whole project. What is more important is when you really deploy the model, you might have to consider a lot of more other things, like what is the size of the model? If your model is like 2 GB, you don't want to copy that around many, many times, right? And how much memory does it consume when the model is low into memory? How much CPU or GPU it uses? What is the time to generate the prediction? And does it require a lot of pre-processing? So all these other things might add up such that there might still a lot of engineering challenge that you have to solve. So yeah, this is more like some questions that we all have to think about. I don't have all the answers, but I hope the talk will give you some useful information. So that's the end of my talk. Thanks.
Thanks, Albert, for his very informative presentation. Any questions from audience? If no, we can have a break of about 20 minutes.